In number 4, we want to use the alternate definition of the derivative to find f prime of 9 for f of x is equal to the square root of x. So here's the alternate definition of the derivative, and remember it's only used to find the derivative at a particular x value, and here the particular x value is x equal 9. So let's just do a little substituting. F prime of 9, that is c is equal to 9 in this case. That's equal to the limit as x goes to 9 of f of x, in our case that's the square root of x, minus f of c, okay, substitute 9, so we have the square root of 9, which is 3, over x minus c, x minus 9. Alright, so this, I'm just going to write a 3 here. Okay, at this point we can substitute in x equal 9 because that would make the denominator 0. Alright, so we're going to manipulate this expression a little bit, and we're going to multiply top and bottom by the conjugate of the numerator. Very often we do that if we want to manipulate an expression involving the sum or the difference of radicals. So let's multiply top and bottom by the square root of x plus 3. That's the conjugate of this numerator. Okay, in other words, the same thing, opposite sign. Okay, so when we multiply conjugates, the middle term drops out, and we're just left with square root of x times square root of x. That's x. The outer plus inner is 0. And the last is minus 3 times plus 3, that's minus 9. And we're dividing by this product, x minus 9 multiplied by square root of x plus 3. Do not multiply out the denominator, because we're trying to cancel the x minus 9, so leave that together as is. Alright? And here we have this x minus 9 in the denominator cancels with this x minus 9 in the numerator. So let's do that. We're left with a 1 in the numerator. And at this point we can actually take the derivative, since we got rid of that x minus 9 factor from the denominator that was making the denominator 0 when substituting in 9. And now we can just substitute in the 9. Okay, so we're taking the limit, substitute in 9, x equal 9, and we get square root of 9 plus 3. Or 1 over 3 plus 3, that's 1/6. Okay, so that's the derivative at x equal 9, 1 over 6. In number 5, we want to use, again, the alternate definition of the derivative to show that f prime of 2 does not exist for f of x is equal to x minus 2 to the 1/3. So let's proceed by trying to find the alternate definition of the derivative and see if we hit a problem, okay, and see why the derivative does not exist. So let me just write that down again. Alternate definition, f prime of c, limit x goes to c, f of x minus f of c over x minus c. Alright, so in our case, we want to find f prime of 2, c is equal to 2. Alright, so we just do a direct substitution, limit x goes to 2. Here's our f of x, just put it here, and here f of c. Alright, substitute 2 in right here. And notice that we have 2 minus 2, f of 2 is equal to 0, so this is 0 over here. Alright, so let's just rewrite that. We have limit x goes to 2. In the numerator we have x minus 2 to the 1/3, and in the denominator we have x minus 2. we can simplify this. This is x minus 2 to the exponent 1, okay, in the denominator, and x minus 2 to the 1/2 in the numerator. Let's just simplify by subtracting the exponents. 1 minus 1/2 is 1/2. So we have limit x goes to 2. All right, so we're just dividing top and bottom by x minus 2 to the 1/2. So we have a 1 up here. And in the denominator, we're left with x minus 2 to the 1/2. Now, what happens as x goes to 2? We get 1 over 0. Okay? So that does not exist. This limit does not exist. This goes to, I'll just write, this goes to 1 over 0, 0 in the denominator. So we'll say that the limit does not exist. All right, so we can conclude that f prime of 2 does not exist. In other words, the derivative does not exist at x equal 2. In number 9, we're asked to give examples of functions that are continuous at a particular point, but not differentiable at that point. So the example that we're giving is, well, we have 3 examples here, and in all cases our point is going to be x equals 0. So these 3 functions are not differentiable at x equals 0. All right, let's just, from the graph, let's just say how we can tell from the graph that these are not differentiable. In these 2 cases, the graph comes to a point. All right, this one comes to an angular point, and here it comes to sort of a curved point. This one's called a cusp, C-U-S-P, cusp. In both cases, the graph comes to a point at x equals 0. Here's x equals 0. So typically that's where the derivative does not exist. The functions are continuous from the graphs. We can see that they're continuous. All right, but the derivative doesn't exist at x equals 0. Here, this graph does not come to a point at x equals 0. But if we look at the graph, it seems to be vertical around x equals 0. So the tangent line is is a vertical line. Actually, the tangent line is the y-axis at the point x equals 0. All right, and the slope therefore is infinite. All right, or the slope doesn't exist. So this one is also not differentiable at x equals 0 because the derivative is infinite at that point. Now we're going to examine the first example and show that the derivative doesn't exist at x equals 0. So we're going to be looking at y equal absolute value of x. So the first thing we'll do is open up the absolute value symbols. All right, so another way of writing absolute value of x is as follows. The absolute value of x is equal to x for x greater than or equal to 0, and it's equal to minus x for x less than 0. Okay, because if x is less than 0, like if x is minus 2, for example, then here this would be minus 2, which would be plus 2. So in effect, we would get a positive value here, just like we do when we take absolute values. All right, another way of looking at this is, you see this says that f of x is equal to x for x greater than or equal to 0. That means when x is greater than 0, we have a straight line here, y equal x. And on this side, we have the straight line, y equal minus x. Okay, that's the x and the minus x. So we see the derivative to the right of 0 is the slope of this line, y equal x, which is 1. The derivative to the left of 0 is the slope of this line, which is minus 1. All right, and let's just write this out. And if we actually want to prove this, we could use the alternate definition of the derivative to show that f prime of 0 does not exist. So that's what we're going to do. We're going to use alternate definition to show that f prime of 0 does not exist. Okay, here's the alternate definition. It's the limit as x goes to 0, f of x minus f of 0 over x minus 0. Now, since this is a piecewise defined function, we're going to do the limit from the right and the left. So first we're going to look at limit, let's say as x goes to 0 from the right, using the top line here for x greater than or equal to 0. F of x minus f of 0 over x minus 0. Okay, so let's just fill this in. To the right of 0, our function is x. F of 0 is equal to 0. So you see we have x minus 0 over x minus 0, which is equal to 1. So the limit from the right is 1. And now let's do the limit from the left. Limit as x goes to 0 from the left. Okay, so that's equal to, just substitute in on the left, the function is minus x, so we're going to put a minus x here. Minus x minus 0, I'm going to leave out that 0. In the denominator we have x minus 0, I'm just going to write x. So we have minus x over x, which is equal to minus 1. And these are not equal. So the limit from the left is not equal to the limit from the right. And that tells us that the limit doesn't exist, or f prime of 0 does not exist. So that's how we would prove that in a rigorous way. In number 7, we're going to show that if a function is differentiable at a point, then it's also continuous at that point. Okay, so let's say we have function f of x, and f of x is differentiable at x equals c, and we want to show that it's continuous at x equals c. All right, so what we want to show is that the limit as x goes to c of f of x is equal to f of c, and that would be enough to show that it's continuous. Now, showing that the limit as x goes to c of f of x is equal to f of c is the same if we just subtract f of c from both sides as showing that the limit as x goes to c of f of x minus f of c is equal to 0. All right, so this is what we want to show. All right, so let's start with that. The limit as x goes to c of f of x minus f of c. And let's just multiply this expression. Let's say if we put this over 1, we'll multiply top and bottom by x minus c. So this is equal to the limit as x goes to c. Okay, of x minus c times f of x minus f of c over x minus c. All right, now here we see this is the definition of the alternate derivative, and we know that this exists, so we know that this goes to f prime of c. That's because of the first part, that the function is differentiable. All right, so that means that f prime of c exists. All right, so this goes to f prime of c. So what is this equal to? Well, this is equal to the limit as x goes to c of x minus c times f prime of c. Well, as x goes to c, x minus c, this part goes to 0. So this is 0 times f prime of c, which is equal to 0. All right, so we showed this. We showed that the limit as x goes to c of f of x minus f of c is equal to 0. So we showed that, which is the same as this. Okay, that the limit as x goes to c of f of x is equal to f of c. And this is what we had to show for continuity. So we're done. Therefore, f of x is continuous at x equals c.